All right. So my name is Daniel Schaaff. I'm the lead DevOps engineer at Cordial, and I'm going to walk you through our journey into EKS, Karpenter, and Bottlerocket. And I will give a small disclaimer here. My French bulldog is snoring very loudly behind me, so I apologize if that's getting picked up. So at Cordial, we create technology for brands to better connect with their customers, help our clients send messages that are more likely to convert because they are based on data. We provide the marketing strategies and the platform for data-driven brands like Revolve, LL Bean, and Forbes to deliver messages their customers love. And we send these messages through multiple channels, including email, SMS, and mobile apps. Like a lot of startups, Cordial started simple. The app began with a monolithic code base and all the components running in EC2 autoscaling groups. We then developed some greenfield microservices and began to run those in Elastic Beanstalk in 2018, moved over to ECS in 2019, and finally to Kubernetes with much success in 2020. At the same time, that original core application continued to run in EC2 autoscaling groups with a static count of instances. As our client base continues to grow, the demand on our applications just grows right along with that. And we're leveraging EKS, Karpenter, and Bottlerocket to meet those demands in a cost-effective and performant manner today. Cordial, we have some key goals to meet with our service. Whenever a client triggers a message send, we need to respond and begin sending that message right away. And the real-time data in our system means that clients can trigger messages at any time. There are a few obstacles we faced accomplishing that with the original messaging components in the EC2 setup. First big issue there was how long it took for the nodes to boot and start our application. As the user data scripts on our instances were responsible for installing and configuring our application environment and all the dependencies at boot. The process would take about 5 minutes to run. And that delay was just too much for meeting our key goals. We couldn't wait a full 5+ minutes to reach full message sending capacity. An example of why that's important, picture flash sale notification on Cyber Monday. Clients are going to be upset if they get that message too late for them to actually take action. So maybe you get the message and the sale's already ended, or maybe that's too late and the company ran out of all the inventory. So key goal of ours is to avoid any delays in send time and then also meet our throughput targets for clients. So how fast we're able to send messages over a period of time. And as a result of that long user data execution time, we were running those core messaging components at peak scale at all times. That means we were overspending on compute instead of using just what we needed when we needed it, which is one of the key value propositions of using the cloud in the first place. And then spot nodes are also a great way to save on compute costs, and were something we wanted to take advantage of. Unfortunately, our node startup time was too long to safely handle those interruptions while maintaining our quality of service. So we began a journey to solve these problems in the original core application, and that started with containerizing the core messaging components so they could run inside our EKS clusters. So at this point, we had experience running a number of greenfield components in Kubernetes, and we believed moving the messaging components over would help us remove that slow node boot issue and enable us to scale the messaging components based on application demand. We did this with a fairly standard setup to start. So you're using EKS managed node groups, the Amazon Linux EKS optimized AMIs, and the cluster autoscaler project to handle adding and removing nodes as needed. And we were able to move those messaging components to Kubernetes in 2021. This migration had some immediate positive results. Our startup times were greatly reduced compared to the EC2 setup because we removed the need for that 5-minute user data script execution. So our app pods were scheduled and they would start very quickly if there was spare capacity on existing nodes. And if new nodes needed to be added to handle the pending pods, this delay was a lot shorter now, usually only 2 to 3 minutes. This is a huge improvement, but still had some rough edges. We wanted to get an even faster node boot time, and we also saw the setup becoming more complex and time-consuming to manage than we had hoped. Our cluster requires each node group to have a bunch of different characteristics for us to do the spot things we wanted, so different types, sizes, purchase types, CPU architectures, all of that. And cluster autoscaler requires your managed node groups to all have the same amount of CPU cores and RAM when it makes its scheduling decisions. So for example, say we want both compute optimized and general purpose instance types available. That would require one node group for C-type 4XL instances, and then a separate node group for M-type 4XLs. And if we also want to mix in 8XLs, then you're looking at 2 more node groups. And then we also needed node groups for both on-demand and spot capacity types. So this gets really messy and verbose quickly. We were managing 14 different node groups just on one of the clusters, and those all need to be updated and maintained independently. And we also had a defined order of precedence we wanted to follow when choosing the nodes when scaling up and down to meet the best cost efficiency. And so we did this using cluster autoscaler's priority expander method. And since our spot node groups had the highest priority, it would attempt to secure a node from them first. And then if it was unable to do so within the max node provision timeout, it would fall back to the lower priority node groups that included on-demand. So this handles seamlessly falling back to on-demand when spot capacity is unavailable, but there is a delay in doing so. And in the end, this just felt really clumsy and time-consuming to manage. Definitely seemed like there had to be a better way. So that's when the Karpenter project came onto the scene. We originally started looking at Karpenter due to its faster response times when adding capacity compared to cluster autoscaler. So Karpenter launches instances directly using the EC2 APIs, as opposed to cluster autoscaler, which will increase the desired count on the underlying autoscaling group. And then you wait for the autoscaling group to launch an instance in response to that desired count change before the node can boot and join the cluster. So Karpenter speeds that up by removing the middleman and launching those nodes directly. So just another thing that can help us meet those key scale time goals for us. And it also removes a ton of the operational burden and complexity that we had with all of those managed node groups. Karpenter is configured with 2 Kubernetes custom resources. It's really easy to set up. The AWS node template resource is used to configure AWS specific settings for the nodes. So think things like what subnets to run in, what security groups to attach, any custom user data, what AMI to use, all those types of settings. And then you have a provisioner resource, which is used to set constraints on what types of nodes Karpenter will launch to handle the pending pods. Now, the provisioner references that node template resource for the node settings, like the AMI, user data, all of that. So this decoupling really simplifies the configuration. You can have multiple provisioners all using the same basic node template. It cuts down a lot on the number of duplicate configurations you need to write and manage. Also has a bunch of different ways to specify limits on the instance types Karpenter will choose. The defaults are suitable for most cases, and I would start there, but you also have the option of explicitly opting into the instance types and sizes you want. So this flexibility is great. It's a lot easier than juggling that huge number of managed node groups. And it elegantly handled our requirements of having both spot and on-demand Graviton and x86 architectures, and allows us to have a large instance size and type diversity to reduce spot interruptions. And we can do that all in this single definition. Karpenter also makes updating the nodes a breeze. So it recently added a drift detection feature. This will automatically drain and replace nodes whose configuration is out of step with the fields in the node template and provisioner resources. So simple example here, when the AWS node template definition picks up a new AMI version, Karpenter will automatically handle draining and replacing nodes running the old AMI. So this makes it really easy to keep nodes up to date in the cluster and completely removed our need to actually take an action to initiate those updates. When we were using managed node groups, we'd have to go through those one at a time and initiate the rolling update. It's not a terrible process, but the Karpenter experience is definitely better. And Karpenter also lets you put a time to live limit on your nodes. So we have ours set to 14 days. And when the nodes reach that TTL, Karpenter will drain and replace them. So it's just another method to keep your nodes fresh, up to date with security patches. And then with the consolidation feature, Karpenter will actively move pods around when workloads can be moved to other nodes in order to better bin pack the cluster and save on compute costs. And it can also actively replace nodes when a cheaper equivalent node can be used. So Karpenter solved a ton of problems for us, but we're always looking for ways that we can do even better on things. And we found one of those in the Bottlerocket OS project. So Bottlerocket is a lightweight, minimal OS that's purpose-built for running containers. And it helped us further reduce our node boot time, simplified our configurations, and also improved our security posture. The minimal nature of Bottlerocket allows nodes to fully start up in 30 seconds or less. Further reduce the startup latency for our workloads when a new node is required to schedule a pending pod. Now, I don't want to shade Amazon Linux. It's not that it's super slow to start, but Bottlerocket is crazy fast and just does a great job here. When we are using the Amazon Linux-based AMIs, there were a few kubelet configurations that we needed to modify that weren't exposed in the EKS bootstrap script. So to do that, our user data used the sed command to modify the kubelet's JSON configuration file in place. This is really error prone, and you need to be really careful here that you don't produce invalid JSON. Mess up will cause the kubelet to fail to start, and your nodes will never join the cluster. No good. And in contrast to that, Bottlerocket uses a declarative TOML config for managing its settings, and it exposed all the kubelet settings we needed to modify. So much easier to maintain. We're less likely to make syntax errors. It's also just a lot easier to read and reason about. And Bottlerocket also has a big focus on security. This wasn't related to helping us solve that scaling speed and boot time goal, but I want to call it out. I think this is one of the best reasons you should choose Bottlerocket OS for your workloads. Just provides additional peace of mind. So the combination of these Bottlerocket security features and our 14-day node TTL helps ensure our cluster's nodes are always up to date and in a secure state. Also extremely simple to make the switch to Bottlerocket OS. We actually made the transition all the way from development to our production environments in less than a week. It's about as seamless as a transition can go. First step, you write an AWS node template for Bottlerocket. You set your AMI family to Bottlerocket, and then translate your user data needs into the TOML config format. Once you have that in place, you just update the Karpenter provisioner to point at the Bottlerocket node template. And Karpenter's drift detection will kick in and handle replacing those existing nodes with the new Bottlerocket-based nodes. I mentioned a few times our sensitivity to node startup time, the ability for workloads to start as quickly as possible to meet those messaging quality of service goals. And this combination of EKS, Karpenter, and Bottlerocket allows us to do just that. Today, we're able to use horizontal pod autoscaler to automatically manage the messaging capacity based on custom application metrics. We're able to size our clusters based on the work they need to do in the moment and can adjust that up and down as needed. And we're no longer running at peak capacity 24/7. And the best part of this is the financial payoff. So all these changes have a real meaningful impact on the cost of running the platform. So Karpenter lets us use spot capacity safely thanks to its fast reaction times, ability to have large instance type diversity. It has built-in termination notice handling, and it seamlessly falls back to on demand when that's required. So we saved 18% on the monthly cost of that original messaging component just with the move to Kubernetes alone. And as our client base and companies continue to grow, the savings have just increased from there. So over the last year, our Kubernetes cluster costs have only grown by 15%, despite both our client and revenue growth rate being much, much higher than that. So it's a huge win, and wouldn't have been able to accomplish that without EKS, Karpenter, and Bottlerocket. And we're not stopping there, continue to build on this strong foundation in some exciting ways. Some highlights here. We're currently processing millions of jobs a month in Kubernetes job objects. We're using Linkerd for advanced network control and observability, managing 50 million active time series in Prometheus. And then using this foundation is helping us iterate quickly as we build out our next generation of AI features. Cool. Well, thank you for your time and attention. I appreciate it.
Thanks so much, Daniel. That leaves us with about 7 minutes for any questions anyone may have.
So I see the first one there. We don't have very many stateful applications. The only one I can think off the top of my head is our Prometheus monitoring stack runs in Kubernetes, and we do have stateful EBS volumes backing that. And then we also have a log aggregation pipeline where we have FluentD as a stateful set there that uses the storage as a buffer. We don't run any database or workloads like that in Kubernetes. Those are all outside that environment.
Okay.
No, so I haven't had any issues at all with Karpenter and the Spot instances. That's been a huge win for us. Kind of that comparison to cluster autoscaler. When we had the priority expander list, we would, say choose Graviton Spot if you can, but then fall back to on demand if you need to. There's always a delay there, so it would try to get the Spot capacity through the Spot managed node group, and if it didn't get it within the provisioning timeout, it would fall back. So that was 10 minutes in our case. Whereas Karpenter just picks that up right away, and it also uses the capacity optimized strategy. So it's optimized to avoid interruptions in the cheapest way possible. So you make smart decisions there. Question there, have you used Bottlerocket for regular EC2 instances? No, so we only use these in Kubernetes. Workloads that we run outside of Kubernetes are getting fewer and fewer by the day, but those are all either on Amazon Linux 2023 or Ubuntu